Hi everyone, I'm Cheryl. We can determine that a function is differentiable if we can express delta z as the partial of f with respect to x times delta x plus the partial with respect to y times delta y plus an error times delta x plus a different error times delta y. If error 1 and error 2 both approach 0 as the change in x and the change in y approach 0, 0. We want to see if this particular function, the function x squared minus 2x plus y, is differentiable. So we need, in our formula, to find the partial with respect to x, the partial with respect to y, and then we want to find these two errors and see that those errors go to 0 as the change in x over the change in x, change in y go to 0, 0. Well, in order to make that determination, let's go ahead and look at those first partials. So the partial with respect to x, we're going to be treating y like it's a constant. So my derivative is 2x minus 2. And the first partial with respect to y, this time I'll be treating x like it's a constant, and so my derivative, or my first partial, will just be a 1. Okay, so what I want to do then is go ahead and calculate delta z. Well, what is delta z? Delta z is the change in the function f of x plus delta x, y plus delta y, minus f of xy. So let's go ahead and plug this in. Now notice what's happening here. I'm going to plug in x plus delta x every time I see an x in my function, and I'll be plugging in y plus delta y every time I see a y. So my function evaluated at this point is going to be x plus delta x, quantity squared, minus 2 times x plus delta x, plus y, so in this case it'll be plus y plus delta y. I'm then going to subtract f of xy, which I know is x squared minus 2x plus y. Okay, so I'm just going to do some algebra on this, and I've got x squared plus 2x delta x plus delta x squared. Distributing the 2, I'm going to have a minus 2x and a minus 2 delta x plus y plus delta y, and I'll distribute the minus across, so I have a minus x squared plus 2x minus y. Now let's see if I can cancel some things. I have a positive x squared and a negative x squared. I have a negative 2x and a positive 2x and a y and a minus y. So I can rewrite this as 2x delta x plus delta x squared minus 2 delta x plus delta y. Okay, now remember what the goal is. The goal is to make this look like my statement. So somehow I want to find my partial with respect to x times delta x. Well, I noticed that I have several terms here with the delta x in, so maybe it'll be helpful to factor a delta x out and see if some of these pieces become clear to me. So I'll have a 2x plus delta x minus 2 times delta x. And then the only delta y term I have is just that single term, delta y. Okay, now remember, I'm trying to get it to fit this form. My partial with respect to x is 2x minus 2, and I see it right here. Here's 2x minus 2. So I'm going to group those together and write this as 2x minus 2 times delta x. Now I still have a delta x times delta x. I also want the partial with respect to y, which is a 1. And I notice that I have right here a 1 times delta y, because 1 times delta y is just delta y. All right, so let's see again if I can match this up. I want the partial with respect to x times delta x. That's this part. I want the partial with respect to y times delta y. That's this part. I also want some error times delta x. Well, that's going to be this piece right here. And my error is going to be delta x in order to make it fit the format. Now notice I don't have an error 2 times delta y. Well, I can make that work by adding a 0 times delta y, and that is this piece of my problem. So my error 2 is going to equal 0. Okay, now, in order for the function to be differentiable, I have to be able to write it in this form, and these two errors have to approach 0 as delta x, delta y approach 0, 0. Well, we know that as delta x, delta y approaches 0, what happens to epsilon 1? Well, epsilon 1, because it's delta x, is also going to approach 0, and epsilon 2 is already 0, so it is certainly approaching 0. And that tells me that my function is differentiable. I hope that was helpful. Thanks.